Okay, in this video we want to do a quick review on antiderivatives and tangent lines, as well as talking about slope fields. So first of all, the derivative is 3x plus sine x, so the function would be 3 halves x squared minus cosine x plus c. Okay, make sure you see that. The next one would be 1/4 x to the fourth minus 4x plus c. This is, review hopefully, so I'm just kind of whipping through this so we can get to slope fields. 2/3 x to the sixth plus the tangent of x plus a constant. Okay. Now the equation of a tangent line, of course, we need two things for every tangent line. We need a point and we need a slope. Well, we know the x-coordinate is 1. And if I plug 1 in, e to the first, the natural log of 1 is 0, so e times 0 is 0. Now for the slope, I need the derivative. So I'm going to need to use product rule. So first, multiplied by derivative of the second, plus the second, multiplied by derivative of the first. Okay. And again, now evaluating that at 1, well, e to the first multiplied by 1 over 1 is e. The natural log of 1 is 0, so 0 times e. So I end up with e multiplied by 0, so the slope, e plus 0. So the slope is just e. So my tangent line is e, x minus the x-coordinate, plus the y-coordinate. Again, that should all be review. Hopefully that's no problem. I just want to, it's always good to look at those. So, a slope field. A slope field is really useful for helping us look at a differential equation and do some analysis of the original function. I'm going to do a simple one, I hope, first, and then I'm going to show you why you need it, because I don't think this first one you're necessarily going to find overly useful. But let's just kind of analyze here a little bit. All right, so I'm going to start by labeling this just a little bit different, just for the sake of ease of evaluating a trig function. Normally, of course, I would just leave them as 0, 1, and 2, but since it's a trig function, let me just change these slightly. Okay, now you'll notice the differential equation here is just the derivative is cosine x, and you're probably already thinking, well, then I know what the function is, but hold on for 1 second. When x is 0, the cosine of 0, and remember derivative means slope, so the cosine of 0 is 1. That means the derivative is 1. That means the slope is 1. Okay, so what I'm going to do is I'm going to go to where x is 0, and I am going to draw a little line that signifies a slope of 1. So every time x is 0, I'm going to draw a little line that looks like a slope of 1. Okay, let me go to the next spot, pi over 2. I'm not going to do anything with this y column yet. You'll see why in a minute. Okay, the cosine of pi over 2 is 0. So now every time that x is pi over 2, I'm going to draw a little slope of 0. I can also do that at negative pi over 2, because the cosine of negative pi over 2 is also 0. Okay, so I'm going to do that over here. Finally, let's do pi over 4. Hopefully you remember that the cosine of pi over 4 is square root of 2 divided by 2. That's about 0.7, so it's still a positive slope, but less positive than 1. So I'm going to draw a slope that's just a little less steep than the one next to it. And of course over here would be the same. Okay. So this is a slope field. That's all there is to it. But here's what I now know. I know that based on my analysis of the slopes, that my original function, whatever it is, and I know you know what it is, has a horizontal tangent, then increases, then starts to increase by less, and then has another horizontal tangent. So if I sketched a sample, it might look something like that. Or I could sketch another sample, look something like that. Or I could sketch another sample and look something like that. Well, all of these look like the sine function, because that's, of course, the function that has a derivative of cosine x. Now, what's different is, and why I drew all these three curves, is because depending on what the constant was, I may have taken sine and shifted it up or down. Now, I think a lot of people look at this and say, well, then what was the point in drawing the slope field if I already knew what the function was? Well, it's a good, fair question. Let me show you. Let's say we had something like this, dy dx equals x plus y, where we don't know what the original function is. This is an implicit derivative. It's a real simple derivative, it looks like, but I don't know what the slope is. Or I'm sorry, I don't know what the original function is. So what I'm going to do is I'm going to use the slope field to give me an idea of the shape of the original function. And in some cases, maybe you can even make a guess about what the original function was. Okay, so I'm going to do this one a little bit differently. Okay, I'm going to start with, this over here is just -2, -1. So I'm going up by kind of a normal scale. I'm going to make x -2. And I'm going to analyze all of the y's. We have -1, 0, 1, and 2. So essentially, I'm doing all of the points. Okay? So, -2 plus -1. Now the slope, remember, is dy dx. So, -2 plus -1 is -3. -2 plus 0 is -2. So I'm just plugging the x and y coordinates into dy dx. Okay. Now I'm going to go to each of those points and draw the slope that's indicated. So I have a steep negative slope here. Still steep, but less negative. Still negative, and 0. Okay. Now I'm going to leave the y's because those are I'm going to need to always analyze those at the same spots, but -1. Okay. So again, I'm just going to plug those points in to the differential equation. So -1 plus -1 is -2. -1 plus 0. -1 plus 1. And -1 plus 2. So now I'm going to go to those points and draw a little line that represents that slope. So slope of -2. Slope of -1. Slope of 0. Slope of +1. Okay. Let's go to the next x-coordinate, which is 0. So 0 plus -1. Do that. So I've got -1 as a slope, 0, 1, and 2. The next let's make x equal to 1. Okay. So 1 plus -1 is 0. I've got 1, 2, and 3. So I've got 0, 1, 2, and 3. Now when these are on the AP exam and you have to draw them, they really don't make you get too exact. They're kind of looking for, is it correct in relation to the other points that you've drawn. And finally, let's go to the x equals 2 line. So -2 plus -1, let me just add those up. So I've got 1, 2, 3, and 4, like that. And there's my slope field. Now again, x plus y is a differential equation. It's an implicit looking thing, and I don't know what the original function was. But now I can make some assumptions about the fact that, it has to have some kind of negative slope, then a horizontal, and then it goes up, and the different curves, something like this, that you can draw are all dependent on what the constant was. And without knowing the constant, you know, it's hard to be able to draw the curve perfectly. Well, it's impossible. But, you know, now at least we have an idea of what the original function looked like. Again, it's as simple as kind of picking those points, and they're always given to you, you know, what points you should plot it, and then plugging those points into the differential equation because this tells us the slope. And then putting those little lines that signify that slope at those points, it gives us an idea then of the shape of the graph. And that's all there is to slope fields.